last week on this example. Okay, can I have a bit of hush, please? Can I have a bit of hush, please? Thank you. I know you're all excited about your assignments, but we've got to work through this. Okay, so last week we looked at stability. Now, essentially, with stability, we use a model problem. Okay, so when we talk about this method is stable, we say where it's stable for this model problem. And that allows us to compare different methods. Okay, so which methods are going to be more stable than other methods? Two main methods of Runge-Kutta, obviously explicit and implicit. We looked at last week how we find the stability function of an explicit method. And I showed you with using the geometric series of matrices and the order conditions what we have. And essentially, it's a very easy set of calculations. So I'm going to show you, I tried to do this last week in MATLAB, and MATLAB was not working on me. So I'm going to hopefully try it again. So here we have a 4-stage explicit Runge-Kutta method. Now, what I'm going to do is show you how to use MATLAB to calculate the stability function. Okay, so I might have to do a bit of Alt-Tab in here because I haven't got my notes in front of me. So what we need is, if I open up MATLAB, okay, first thing I'm going to do is I'm going to enter the A, B, and C arrays. So remember, A, B, and C have just come from the butcher tableau. Okay, so for this expression, okay, 4, 0, 2 9ths, 1/3, 4 9 0. Okay, so that's my A matrix. Okay, so straightforward. And notice I'm in the command window. I haven't opened up. I haven't started a new script. Essentially, this is kind of like a notepad. It's like a scratch pad for the calculations. These, oh, I don't make it easy, do I? 7 24ths, 1/4. That's 7 24, 1/4, 1/3, and an 1/8. And that's a column vector, so I'm just transposing that vector there. And C is 0, 1/2, 3/4, and 1. And again, that's a column vector. Okay, so I'm just going to check I've entered in A, B, and C, okay. So B and C. Okay. Right, and the steps we do is, okay, the first K1 for an explicit method is always the Euler method. Now, Euler method has a stability function 1 plus Z. So I know, but this method is going to have a stability function of 1 plus Z plus something Z squared plus something Z cubed plus something times Z4. It's not going to go any more than Z4 because we've only got 4 stages. At most, this can be a 4th order method. The coefficients of Z5, Z6, etc. will be zeros. Okay, so what we do is I'm going to use the rats command. Now, what this will do is whatever number appears in the bracket, MATLAB will attempt to put it as a rational fraction. Okay, and what we do is we calculate the coefficients of our Z squared, Z cubed, etc. as B transpose times A to the power 0 times C. Okay, this comes from the application of the geometric series of matrices and an order condition. Okay, so this is the half is our coefficient of Z squared. We already know it's 1 plus Z, and the next one is going to be something times Z squared. Okay, so the calculation is B transpose times A to the power 0 times C. So that's coefficient of Z squared. Coefficient of Z cubed is exactly the same, but I've just increased the power of A. Okay. And we get 3/16. Do the same for Z to the power 4. 1/48. With that z to the power 4, we know our method can only be up to 4th order. If I did try, and what's the coefficient, calculated coefficient of z to the power 5? That's 0. Try z to the 6, 0. Okay, so you can go on if you want. So to be honest, you don't have to remember when to stop. Just keep going until you get 0. Okay, so what does this mean? Well, here, this is my z squared. This is my z squared exponent. Coefficient. This is my z cubed coefficient, and this is my z to the power 4 coefficient. Remember, we're comparing this against a model problem. The model problem should behave like the exponential function. That's what we're aiming for. Now, the expansion of the exponential function is 1 over n factorial, where n's our term. Okay, so we should have 1/2. So the coefficient of z squared should have been 1/2. Coefficient of z cubed should be 1 over 6. And that should have been 1 over 24. So what we can say, I'm just going to go back to the slides briefly for this. Okay, this gives us this stability function. Okay, that's the stability function of our method. This is what we're aiming for. This is the actual behavior of the model solution to that model equation. And you can see these two functions agree up until the z squared term, but when it comes to the z cubed term, they disagree. So we can say this method is second order. Okay, and you can actually plot the stability region, and I'll show you how to do that. Okay, so what I'm going to do is go back to the MATLAB. To plot the stability region, we have to generate an array of z values. Now, z will be a complex number. So complex number has a real part and an imaginary part. So I'm going to say x is going to be my real part. So I'm going to create an array of x values. Say, I'm mainly interested in the left-hand plane. Okay, I'm mainly interested in the left-hand plane. If you've done Leader's questions on her assignment, you'll be familiar with this. And in the y direction, actually, I'm going to change x direction to be the same as the y. Okay, so x is my real part of z, y is my imaginary part. What I'm going to do is I'm going to use a mesh grid command just to create, at the moment, if I go whos, okay, x and y are 1 by 101 arrays. Okay, if I use a mesh grid command, all this does is put x and y. Okay, if I do whos now, makes x and y as 101 by 101 arrays. So instead of being a one-dimensional vector, it's now a two-dimensional matrix. Okay, so in order to generate my complex numbers, z is equal to the real number x plus the imaginary number y. Hey, thank you. Okay, so that's generated my imaginary my array of complex numbers. Okay, so if I want to plot, let's say I want to plot the Euler method stability function. That's just 1 plus z. Okay, so I'm going to actually say, yeah, so Euler method is 1 plus z. Second order Runge-Kutta will be 1 plus z plus 1/2 times z squared. Third order will be the same, plus 1/6 times z power 3. And fourth order will be the same, z to the power 4. So R1 is the Euler method, R2 is the second order, R3 is third order, R4 is fourth order. Now, if I just I'm just going to show you the surface plot of the Euler method. Oh, well, I won't show you that. Oh, no, what I should do is we're looking for the modulus of the surface plot. Okay, so it looks like there's a bowl shape. I've used quite a lot of terms in my X and Y, hence why it's... okay, so, well, actually, this one's kind of like a cone shape. Second order would be a bowl shape. Remember, the area of absolute stability is where this function is equal to or less than or equal to 1. So what I'm going to do is I'm going to take a slice along the z equals 1, or the modulus of z equals 1. Okay. To do that, we use the contour command. Okay. So I'm going to do a contour plot of xy abs r1. Okay. So what do we get here? Okay, we get a series of concentric circles. So these include all of them. I only want the one which is sliced through where this abs r1 is equal to 1. So what I do here is there's an option in the contour plot, and for some reason you just put 1, 1 in square brackets after that. What that does is that'll only give me a circle where the absolute value of the stability function is equal to 1. Okay, so I don't know whether you can see that very well. Okay, that's actually a circle. I've skewed the axes a bit, so it's squashed down, but that should be a circle. Okay, notice MATLAB isn't as good as MATLAB for doing this sort of plot. You notice, okay, this is my 0 line. Okay, so that's when the real number part is 0. Okay, that's my, sorry? Oh, sorry, who's speaking?
You said MATLAB is not as good as MATLAB.
For this type of plot. Sorry?
MATLAB compared to MATLAB.
Okay, switch them around. You know what I mean. Sorry. What did I say? Did I say MathCAD's not as good as MATLAB? Okay, I'm sorry. Which one? MATLAB? MathCAD is a better one. It's been a long term, hasn't it? Okay. And there's my real number line. So anything on that line is imaginary part 0. We're interested in anything to the left of this line here. Okay. If I do some holds on, okay, I can do the same plot. So this time, second order, third order, and fourth order. Okay, I've done them in snazzy green, which is probably the worst color I could have done them in. Let's see if I can just change that. There, yeah. In the notes, well, in the electronic version of the notes, you'll see. So this is the one on the inside is first order and concentric going further out. And that's the order stability regions for explicit methods. Okay, so what I'm going to look at now is implicit methods. Okay, so this is the other version. Okay, that's one type. This is the other type. We saw last week that the general Runge-Kutta method has this stability function. A couple of things to note. I, or bold I, is a vector of 1s. Now, if we use Cramer's rule on this, so Cramer's rule uses determinant of a matrix over the determinant of another matrix to solve the system. Okay, we get this. Okay, this will allow us to determine what's the stability function of an implicit method. Okay, there is one fudge. It's kind of a little fudge, but the reason we do it is to make it make writing down of Cramer's rule easy. Now the fudge is this 1 times B transpose This essentially means I've got a diagonal matrix with the values of B on the main diagonal. So in other words, 1 times B transpose equals that. It's a fudge. The reason we do it is so we can write our stability function in a nice, concise way. If it's not massively it doesn't follow completely from Cramer's rule, but it just means, means it simplifies everything. So where you see the vector 1 times B transpose, it means we have a diagonal matrix with the main diagonals being the values of B. So if we had a 2-stage method, B1 and B2, okay, our main diagonals, elements of B1, B2. Okay, implicit method. I mentioned a few weeks ago when we first dealt with implicit methods, we got much better stability properties than explicit methods. And one of these properties it can have is the property of astability. Now, astability essentially means the stable region is everything in a negative real plane. So everything to the left of the plane, if that's stable, that means we have astability, which means there's no restriction on your step length, which is brilliant. It means we can cut down significantly on the number of calculations we have to perform. Of course, implicit methods are more computationally expensive than explicit methods, but they have better stability, so we can use less steps. Okay, so essentially that's what astability means. A common an exam question which always pops up, bit of a trick question. Quite often you'll see an explicit method and the question is determine whether it's astable. Quite simply, an explicit method cannot be astable. So you can write in your exam question, in your exam, you say, well, this is explicit, that can't be astable. Okay. Quite a common exam question. I've seen pages and pages of algebra, people trying to work it out. It's like, well, but it can't be. So, okay, how do we determine whether an implicit method is astable or not? Well, what we'll do is with Cramer's rule, I'm just going to go back a couple of times, we end up with a fraction. Okay, you can see we have a determinant on the top of a fraction and a determinant on the bottom. Okay. If we call the function on the top nz and the function on the bottom dz, I call them n and d because numerator and denominator, we can define this polynomial in terms of y. So y is just some variable. So we define a polynomial EY by this. Okay, so it's the denominator function where we have the I is the imaginary number times our variable y, multiplied by the same function, but this time it's minus I times y. Okay. Minus the function on the top in terms of IY, multiplied by the function on the top in terms of minus IY. This will give us an algebraic equation. And what we can say is, this is given without proof, by the way. The proof of this is horrible. If all roots of the denominator function are in the right-hand plane, that means you calculate the roots of d. If the real number part of the roots of d is positive, okay, so that satisfies number 1. And if this EY function is positive for all y in the real numbers, then we have an astable method. So there's 2 things we have to check. One of the roots of the denominator function are in the right-hand plane, and the other is that this function is always positive for whatever y, then we have an astable method. If either of these 2 aren't satisfied, we haven't got an astable method. Okay, so let's have a look at this method. Anybody recognize that butcher tableau? It's got surds in it, hasn't it? Okay, so here we've got a method. How many stages? How many stages of this method? Thank you. Don't worry me. You got your assignment in a couple of days. Okay, astable method, implicit or explicit? Clearly implicit. Obviously, I wouldn't be going through it if it wasn't. Okay, so what we do, our A matrix is this quadrant up here. And remember that 1 times B transpose are the B values, which is in this case a half and a half, on the main diagonal. Okay, so just going to go back a couple of slides. Here, what I do is I take this function. By the way, this function is given if it's asked for in an exam. You don't have to remember this. You just have to be able to apply it. Okay, so that's simply applying that stability function. Identity matrix plus Z multiplied by IB minus A. That's on the top. So that's your NZ. Your DZ is simply identity matrix minus Z times A. Remember Z is H lambda, but that doesn't really matter. We always quote, we have our stability function in terms of Z. Okay, with this, excuse me, with this sort of question, you can use symbolic maths in MATLAB to actually sort of reduce it. You can do that, but seeing these are only either 2 by 2 or 3 by 3, it's not that difficult to actually do it by hand. So either or, don't mind if you use MATLAB or do it by hand. So this is an example of hand calculation. Okay, so each successive step, I've gone further. So the top one is just straightforward. Okay, examining what the contents of the square bracket is. Okay, so determinant of a 2 by 2 on the top, determinant of a 2 by 2 on the bottom. Okay, so you know how to work out the determinant of 2 by 2 matrices. And in the end, you'll get a polynomial function on the top, and we'll get a polynomial function on the bottom. Okay, so here you have your NZ on the top, and this is your DZ on the bottom. Okay. Anybody sort of a bit unclear about that? Just a bit of algebra, really. When you're in an exam doing this sort of question, take your time. It's so easy to make a slight sign error or a slight mistake. It's actually, to do a determinant of 2 by 2s, that's what we taught you in the first year, so you know how to do it. Just take your time. I should practice what I preach, actually. I'm always getting these sort of little mistakes in these questions. Okay, so calculate the roots of the DZ using whatever method you want. MATLAB, remember, in the exam, it's taking place in the lab. You'll have MATLAB available for you. So, you know, use all the tools available. So the roots of DZ are 3 plus I root 3 and 3 minus I root 3. We're only interested in the real part of the roots. So both of them are 3, both are positive. So that's the first criteria satisfied. Okay, the second bit, this is the trickier step, calculating EY. And again, this will be given to you. Okay, so don't feel the need to memorize this, although you by the time you finish revising, when we do it at the end of term 2, you should know this sort of off by heart. But, okay, so the D function was 1 minus a half Z, and just checking, sorry, 1 plus a half Z plus a 12th Z squared. Okay, recall we've got IY. Okay, when you square I, you get minus 1. So the main mistake that people make on this sort of question is the negatives. Okay. And similar with the N. Okay, so here we got 4 functions. Okay, multiply out the brackets, we get this horrible, horrible thing, but it's easy algebra, it's just long. Okay, if you go through and cancel all of those terms out, at the end of the day, in this case, EY is equal to 0. Now, the second criteria that was EY was greater than or equal to 0. Because it's equal to 0, it's satisfied. So since EY is greater than or equal to 0, the roots of DZ are both in the right-hand plane, we can say this method is astable. Oh, sorry, I haven't got my... Hang on. Sorry, I haven't got my notes on this. It's what we sort of fudge. It just makes it's kind of thing. If you want to find it, okay, Maggie just asked a question. It's quite a valid question. Where do we get? Where does this come from? Okay, it's a fudge. Quite often in maths, we have these things which we want our equations to look nice and simple, but quite often they're not nice and simple. Okay, this, if it was written out properly, this would be sort of a lot more untidy than it is. So what we'd say is this 1 times B transpose is this matrix here. It's a fudge. It just makes it nicer. It's mathematically correct, but it's still a fudge. Right, what time are we on? Okay, what I'm going to show you is a couple of little tricks in MATLAB. Okay, hopefully this will work. I didn't sort of practice these beforehand, so we'll have a go at them. Okay, this stage here is the niggly stage. Okay, this is quite, sometimes this can be quite niggly to do. So what I'm going to attempt to do is do it in MATLAB. Now, normally I practice these things before, but I haven't, so hopefully this all goes right. So here we have the function n is 1 plus a half z plus a 12z squared. So what I'm going to do is show you how we can use MATLAB to do all those calculations. Okay, I'm just going to clear stuff. Okay, I think I've said to you a number of times that MATLAB isn't, did I say the MATLAB? Yeah, MATLAB is not the best symbolic maths package, okay, but it can do stuff. So I'm going to see if I can do stuff with it now. Okay, so what I've done here is I'm saying, okay, Z and Y are symbolic variables. Okay, so I'm going to use symbolic variables with this. And in this particular case, our n function was 1 plus a half z plus a 12z squared. So I'm going to define a function 1 plus a half times z plus a 12 times z squared. Yeah. Okay. This inline command is a quick way of defining a function. Especially useful when we're dealing with sort of symbolic variables. Let me spit that up. Okay, and I do the same for the d, the denominator. Okay, so that's 1 minus a half z. So it's almost the same, really. So rather than type everything out again, I just press the up key. And I'm going to put a semicolon at the end. Okay, so I've defined 2 functions, n and d. What I can do with this is use symbolic maths to actually calculate what n I times y is. So what I can do is I can calculate what's the value or what the polynomial function EY is? Okay, so just to remind myself, I said it's given to you. Okay, so it's DIY times D minus IY. So I'm going to say E equals D I times Y times D minus I times Y minus N I times Y times N minus I times Y. We got that right? You may be wondering, what's the 1 in front of the I? MATLAB's a bit funny with this. Sometimes the I works on its own. Sometimes you need the 1 in front of it. I don't know why. Okay, it's one of those little idiosyncrasies in MATLAB. Okay, so if I type that in, it's done all the work for me. Okay, what I'm going to just do is put that at the top so you can see. If, in this case, it's quite simple, it just all cancels out to 0. Quite often, that's going to be a polynomial function, okay, and it will return a polynomial function. It's up to you to determine whether that polynomial function is always greater than or equal to 0. But in this case, we got E0. Now, this comes to the question. In an exam, you state you must show all your working. Okay. If you were to put down a value for E and it was incorrect, and you just said, I use MATLAB to calculate this, I'd have to give you something like 0 out of 4. Okay. You can use this to check your answer, but you must show in an exam your steps. Okay. It's probably enough to actually show if you write down the commands you did here. So if you were to write down this, that, and the other, where is it? If you were to write down these and that, you could say using MATLAB, here's the commands I used, blah, 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 and it'll give you the number out. That's fine. Because if you made a mistake, let's say I changed that to be -1. Okay, say that was -1 by mistake, and you carried on through and you stated your answer, you just lose that 1 mark for that 1 mistake. Okay, so when we say show all your working, if you do use a maths package, for example, MATLAB, write down the commands. Then if you have made a mistake, we can see where you've made the mistake. Okay, what I was planning to do is actually go through a couple of exam papers. But the problem is we've got 10 minutes left. I don't think it's worth starting an exam paper because it'd probably be worse to get halfway through. I'll distribute the exam papers, the questions if you want, and you can have a go at them. And maybe we'll look at them next week. But I don't think there's any it's worth actually starting this now at all. Okay. So in that case, say goodbye to the internet.